This is the fifth and final lecture on general relativity that I am going to give. Today we will discuss the solutions to Einstein's equations with certain types of matter. So, the quantity that is important to bring up in this context is the stress energy momentum tensor of the fluid distribution, in the presence of which we want to solve the Einstein's equations. It turns out that even if you keep the fluid stress tensor simple, like that of a perfect fluid, the equations are interesting enough, or complicated enough that it takes some time to go through the math. So, we will use that as an example. But perfect fluid is still a very relevant fluid because there are distributions in the universe that are well described by this stress tensor to a good degree of approximation. So, as you already saw, the components T alpha beta of a perfect fluid stress tensor in these T x y z coordinates are these, given by this 4 by 4 matrix, where all the non-zero components are along the diagonal, T 0 0 being the energy density rho, and T x y T y y T x x T y y T z z being the fluid pressure. There is a nice way for rewriting this expression and that is given in this red box in terms of rho and p. Okay, the first term here is rho plus p multiplied with the components of the 4 velocity vector that is momentarily co-moving rest frame with respect to the fluid element of interest, because T alpha beta are the components of the stress energy of the fluid in that frame. And this is a product of u alpha with u beta. There is a second term which is pressure times the component of the inverse metric, so g alpha beta. And so, in flat space time, a familiar terrain, you will notice that the the time component of the stress tensor is just rho plus p times this quadratic in the time component of the 4 velocity vector plus pressure times the inverse g 0 0, or therefore eta 0 0, because we are in flat space time, flat space time. So, but u 0 square is just unity, and so from the first piece you have rho plus p, and from the second you have negative p, because eta 0 0 is negative 1, and that leaves you with T 0 0 being just rho. So, this expression actually reproduces what I wrote in this matrix form, right. So, T 0 0 is indeed rho. We apply the red box again for calculating the spatial component, okay, x x T x x, and because we are in the momentarily co-moving rest frame of the fluid element, u is completely aligned along the time axis, which means that the x, y, z velocity components of the fluid are 0 in this frame. Therefore, u x, u y, u z are zeros. Hence, this first term does not contribute at all to T x x. Okay. But g x x is not 0, that is simply unity because it is eta x x. So, that is how you get T x x is equal to pressure P. This is what you see here, T x x. The same logic will apply for T y y and T z z. You can also convince yourself that the off diagonal components will all be 0 in this special case. But this is a handy expression. In fact, it is more general than just flat spacetime. You can apply it to curved spacetime as well, where g alpha bit can be more interesting, and similarly for u alpha u beta. So, let us pick up one such metric, something you saw in the lectures here, namely the spherical symmetric static metric with line element ds square is equal to negative e to the 2 phi dt square plus e to the 2 lambda dr square plus r square d omega square, where d omega square is the line element on a unit radius 2 sphere, or just unit 2 sphere, or S2. I have kept phi and lambda general so far, but they are functions of the radial coordinate for static spacetimes. Now, for spherically symmetric static stars, the fluid has no motion, and so the fluid velocity normalization tells us u dot u is equal to -1. That in turn implies that our g00 multiplied with u0 square is -1, but g00 is negative e to the 2 phi. So, the negative cancels the negative here, the -1 here, and the negative of 2 e to the 2 phi, and so the square root of u0 square will just be the square root of 1 over e to the 2 phi, which is e to the -phi. So, you can work this out and convince that this normalization here for the 4 velocity vector tells you that the time component of the u vector is just e to the -phi. And to get u with 0 down, you apply on you contract u mu with g0 mu, and that will tell you that u0 with 0 down has to be negative e to the phi. These will be useful in a moment. Thus, the non-zero stress tensor components for perfect fluid in the spherically symmetric static geometry will be, again using the red box, T00 is equal to rho plus p u0 squared plus p times g00, but u0 we have worked out is e to the -phi. So, u0 square will be the square of that. So, the first term here is just rho plus p times e to the -2 phi, and g00 for us is the inverse of this object. So, that is simply negative e to the -2 phi. P is then just a spectator. So, if you combine them, you find that the p terms cancel off, leaving you with rho times e to the 2 phi. Similarly, you can compute space component. So, TRR, that will be rho plus p UR plus p GRR, and because this is static, u once again does not have any spatial component. So, UR is 0, and that tells you that GRR is the only remaining interesting piece, and that will be the inverse of this component here. So, it will be e to the -2 lambda, and that is because e to the 2 lambda is GRR with both r down, okay, subscripts. Here what we have is the inverse of that. So, this will be just p times e to the -2 lambda. Why are we using this? The reason we are using this is because these components will be helpful in the Einstein's equations to figure out the curvature tensor components. So, that is where we will proceed in a couple of slides. By the way, if you are using the form of Einstein's equations where T mu nu has mu and nu down, then you will have to go from what I just calculated to those components with indices down. So, recall the u0 components from the past. So, t with the time components down will be just rho times u with zeros down. So, that will give you rho times e to the 2 phi, because u0 square where u0 is down is just negative e to the phi square. So, that checks out, and then TRR with RR down can be obtained by two contractions of the metric with T mu nu, where one of the indices on these metric components is the radial component. But on the previous slide you would have seen that T mu nu is non-zero only in special cases where mu and nu represent diagonal components, and that will leave you with only this non-zero piece in the summation once you employ the Einstein convention. So, therefore, the GRRs are just E2 lambdas, and TRR on the previous slide we worked out is P e to the -2 lambda. So, this gives you P times e to the 2 lambda for TRR. T theta theta you can verify is just r squared times the pressure. By the way, here P is always the pressure in the context of this fluid, and T phi phi is just sine square theta times T theta theta. So, this gives you all the non-trivial components of the stress tensor of our fluid under this symmetry. So, these components and the corresponding Einstein tensor G mu nu's set up the three independent Einstein's equations as one can check. but there are 4 unknowns. Okay, what will be the 3 Einstein's equations? Of course, the time component of the Einstein's equation, the radial, and then the theta. Okay, phi is related to theta. So those are the 3 independent Einstein's equations. What is the problem? The problem is that there are 4 unknowns to solve for. Phi and lambda coming from the metric, rho and p coming from the stress tensor describing the fluid. So clearly there is a problem. Where do we get the 4th equation from? But if you have done fluid dynamics, even in flat spacetime, you realize that you need another equation to specify the nature of the fluid, and that is the equation of state of the fluid. We dealt with examples of equations of state of different fluids like dust, radiation, dark energy, right. So you need an equation of state, otherwise you are not describing the fluid completely enough. So thankfully this is not a problem. So once you specify that equation of state, namely P, the pressure as a function of density and entropy, which oftentimes will just be pressure as a function of this should be pressure as a function of rho, the density. That is because entropy will turn out to be in many interesting cases just a constant or too small to be affecting anything. This will happen, for example, for neutron stars. So then this is that 4th equation. So you have 4 unknowns and 4 equations to solve for them. So that sets up our problem in differential calculus, right. So notice that we started with this fancied object tensors, but ultimately we are able to do mathematics involving differential calculus by dealing with the components of these tensors, right. Sometimes you can get another equation which is not really independent, but oftentimes easier to solve, namely an equation that comes from the conservation of the energy momentum tensor. Remember, this is something that the Einstein tensor also satisfies, right, because of the Bianchi identities. So T mu nu should be divergence free. That is what this covariant derivative with nu contracted with nu on T mu nu equal to 0 means. If you solve this for the stress energy tensor I introduced a couple of pages ago, you will be able to confirm that rho plus p times the radial derivative of phi, which comes from g00, should just be negative of the derivative of pressure with respect to radius. The other nice thing with this symmetry is that only radial derivatives survive, right, because the space-time is static. And the fluid we are dealing with is static, although it can be relatively easily generalized to non-static fluid, by the way. For example, to deal with the geometry around the sun, where the sun itself has material churning, upwelling and downwelling in the form of plasma, for example, right. But for this first example, we will keep things simple. So there are no time derivatives. There are these radial derivatives. So this is equation 1. We solved the vacuum equations in the past to figure out GRR, remember, which is how we got the Schwarzschild metric. So if you take a Q from there, you can guess that GRR should be something like 1 minus, this should very likely, again because of similarities with Schwarzschild metric, most likely have a factor of 2 times m as a function of r divided by r. Okay. But m need not be a constant, because now we are inside the fluid distribution, we are not in vacuum space-time. Okay. That is the space-time with which we dealt with in the example of the Schwarzschild metric. And there m is a constant. Okay. It may still mean the mass of a star, but we were exploring geometry outside of the star, where we took the space-time to be vacuum or approximately vacuum. So there we had 2 times m here for GRR, okay, and that m was a constant. But here this will be 2 times m, where small m may not be a constant, because it may in fact change with the depth inside the star at which point you are located, right. Fine. So now if you go back to the time equation of Einstein's equations, right, you can verify that you will get this. The time piece of the stress tensor is the energy density, right? And but on the left hand side from the Einstein tensor, you can work things out to show that you will get the single derivative of this mass function m of r with respect to the radial coordinate. Okay, so that will be equal to 4 pi r square times rho. Now this is very reassuring because this has a nice Newtonian limit, right, where you know that if you integrate this quantity in radius, then you should ultimately get a value for the mass of the star that is enclosed within some radius big R, right, small r equal to big R of that radius. And rho is the energy density describing the matter inside that radius of interest. So this conforms with that expectation. Now similarly show you should show that the RR component of the Einstein equation gives you this third equation, where the phi derivative of the radial derivative of phi coming from g00, which by the way is related to oh actually let me just leave it at that, right. So which comes from g00. So the radial derivative of phi can be related to this mass function mr and the pressure coming from TRR in this fashion. Okay. So take this as given or work them out from Einstein's equations. So you have three equations here, but the nice thing is that you can combine equation 1 and equation 3 to get rid of d phi by dr, so that you get what is known as the Tolman-Oppenheimer-Volkoff equation, which is the title of this slide. In short, TOV equation. Okay, this relates the radial derivative of the pressure to the mass function and the pressure and the density of the star. All right. So this is an important equation in this box. So ultimately, again, we have to pick three independent equations because there are three variables, as we have noticed finally that we have boiled things down to, and that is because we traded off one of the four variables in the past, namely phi, in terms of the other variables by using some of these equations. So they didn't come without any cost. We traded off with equations, but ultimately the three variables are rho and p and m, the mass function. Okay. So what are the equations we choose? You can use the second equation here, which is an equation of the mass function. You can use equation 4, the TOV equation for which involves the derivative of the pressure, and the third equation could be the equation of state. That is something we cannot get rid of. That has to be there. That has not been accounted for by any other way here, right? So three equations and three variables to integrate, right? But how do you do this integration? Are there examples of equations of state that can be solved for exactly analytically? And the answer is yes. There is an unphysical case where rho is a constant everywhere, and that can be solved for exactly. And then as the second solution is something that was found in the 80s by Bugdell. So that's called the Bugdell's star. That is actually realistic. Well, we don't know whether physically such an equation of state is realized, but it is a relativistic equation of state and it can be solved for exactly. It does give some useful limit for the radius of stars, but for known realistic cases of equations of state, you will have to integrate these equations in radius, and that can be done in steps. So you use the equation of state to replace, for example, the rho, the energy density everywhere, with p, right? And then you integrate in steps, okay, simultaneously. For example, outward from r equal to 0, the center of the star, to the surface of the star, by taking small steps in r, the radial coordinate, and you keep computing the pressure at the revised value of the radius, so slightly outward from the star to begin with, right, from the origin, not the star, from the origin of the star, and similarly the mass function at that same radial step. So this is how you keep integrating outward in the radius and figure out how the mass changes with radius, the density changes with radius, and the pressure changes with radius. Okay, the pressure and density change with radius have to be consistent with the equation of state. So this is how in fact we solve for various interesting stars, the interior of the stars, right. Here I show on the left panel how the pressure changes with density for various equations of state, and one simple case is a polytropic equation of state where the pressure is proportional to a power of the density, okay, and gamma is that exponent. In this case, this blue plot, okay, somewhat cyan actually, is for a value of gamma equal to 2. There are multiple other equations of state that I have shown that differ somewhat from this gamma equal to 2 polytrope, like GNH3, H4 and so forth. These are different neutron star equations of state. I am going to come to neutron stars later, which is why I am preparing you by showing this in advance. So, at smaller densities the pressure is somewhat lower than gamma equal to 2, but at higher densities the pressure becomes larger. All right. So, and these other equations of state actually come from applications of nuclear physics that study the interactions of nuclei, nucleons actually, which are relevant to understanding neutron star matter. But for solving any of these equations, remember you have to worry about boundary conditions. Now, in this lecture I will not have time to delve into the details of that, maybe you will see them in another lecture. But you have to assume some central density and a concomitant central pressure consistent with the choice of your equation of state, and then of course at the surface the pressure has to vanish. But in solving these equations you have to worry about continuity. So, you cannot suddenly turn off the pressure at the surface. So, you have to do it gradually, and that is also consistent with what is realistic. So, you have to pad the surface of a star typically with an atmosphere that gradually becomes tenuous and the pressure gradually goes to 0. So, there are some details and some care that you will have to bear to integrate those equations to come up with configurations of realistic stars. But there is some freedom in, for example, choosing the value of your central density, because there are different stars with different central densities that give rise to stars of different masses and sizes. And that is what is captured in this right plot of the mass of the star as a function of the radius of the star. In this special case we are talking about neutron stars, where the star is primarily composed of neutrons with some small fractions of protons and electrons. But of course, these are all neutral stars. Now, the type of mass that is plotted here is technically the Adium mass or the Arnold-Misner mass, Arnold-Misner mass. So, I am not going to be able to go into the details of how this mass is computed, but essentially it is computed by looking at the how strongly the gravitational field falls up at infinity, where we assume that at infinity what we have is flat spacetime. So, these spacetimes are all asymptotically flat. These radius values that you see are small, meaning they are just in kilometers, and you know right away that they cannot describe stars like our sun, because stars like our sun would have much larger radii in like hundreds of thousands of kilometers. The radius of our planet, the Earth, is about 6,400 kilometers. So, whereas these have only radius of 10 kilometers, 12, 13. So, what is going on? These are obviously highly compressed objects, and especially given that the mass they are capturing is of the order of 1 to 2 to 3 solar mass. So, that is what happens, as we will see in a moment. But what are these different curves? Let us look at this solid black curve for the gamma equal to 2 polytrope, right. This is what you get by using this gamma equal to 2, this cyan equation of state. But if you choose a given central density, somewhat so choose a specific central density and then integrate the TOV equation and the other accompanying equations forward in the radius, and you will build up a star with a mass, in this case of 1.5 solar mass, with a radius of something like 10.2 kilometers. Choose a different central density, for example much smaller central density, and you will get a radius that is like 15 kilometers and with a mass of some lower than 1 solar mass. So, you choose different central densities to build up stars, all stable stars here with different mass and radii, masses and radii. If you use a different equation of state, notice that this mass radius plots can be very different. Okay. In other words, if you had multiple observations of neutron stars, by observations here we mean the observation of their mass and radii, right? Then let's say you make a scatter plot of those masses and radii, and by observing that scatter plot, you will be able to tell which one of these equations of state is really obeyed by neutron stars in nature. And of course, we are assuming that all neutron stars are constituted of the same equation of state. But this is an open problem. So, one of the purposes of these lectures was to bring you close to research problems. So, this is a research problem where we don't yet know what the equation of state of a neutron star is. We have some hints, but we don't know which of these curves is actually obeyed by neutron stars in nature. How do we explore that? Maybe I'll have occasion to give you some clues to that later in this talk. So, white dwarfs and neutron stars, how do they form? When a star exhausts its nuclear fuel, it leaves behind a white dwarf, neutron star, or a black hole as its remnant, depending on the initial mass of that main sequence star. So, in the absence of enough thermal pressure, that is when the fuel is all burnt out, it is just the electron or the neutron degeneracy pressure that supports the star against further collapse due to its own gravity. But provided the initial mass is not large enough, that is below about 30 times the mass of Sun. If the initial mass is greater than that, then these degeneracy pressures are not enough to stall that collapse, and you have a black hole form as a remnant, okay, from basically the core of that star. So this is how these compact objects form, the white dwarf, neutron star, black hole. Yes, if the star is less massive than about 10 times the mass of Sun, then most likely the remnant will be a black hole. If the initial mass of the star is between roughly 10 to 30 times the mass of the Sun, then the remnant will most likely be a neutron star. Okay. Higher than 30, black hole. So, electron degeneracy pressure is what supports white dwarfs against gravitational collapse. But quick back of the envelope calculation here, which I've taken from Bernard Schurz's book, which is one of the books I introduced earlier in my lectures, is the following. So, how much pressure does a gas of electrons exert, essentially arising from the uncertainty principle, which tells us that you cannot pack more than one electron into the same state, and here by state I mean state of momentum, space, and also spin, right. So, when you account for the fact that electrons come in up and down spins, then you can have at most 2 electrons in that same momentum phase, coordinate momentum phase space, right. So, so that then creates this pressure. So, for white dwarfs which have an initial mass less than about 8 to 10 times the mass of Sun, you are confining these electrons into a spatial volume, let us say V. And if so, then the momentum of this electron is uncertain in this range delta p, which is given by the Planck constant divided by delta x, okay, that is the spatial latitude afforded by this volume. So, that goes like in dimensional analysis the cube root of the volume in the denominator. Okay, so, that is what you have here, just the uncertainty principle. Now, the number of momentum space states that you have between p and p plus dp for this electron will be say dn, and that is the shell in this momentum space, okay, which is 4 pi squared dp divided by the cell delta p cubed, okay, that is the volume of this small cell with momentum uncertainty delta p. So, this, but then you can replace delta p in terms of the Planck constant and the volume available to this electron, right. So, then you express the number of cells confined in this shell of dp thickness and volume V as such. But because each of these cells can accommodate up to 2 electrons with up and down spins, you will get a this factor of 4 converted to factor of 8. Continuing, So, this is the number of cells that will be available to you, 8 pi p square v dp by h cubed. Now, so the number density of electrons occupying states all the way up to Fermi momentum in this star, and let us say the Fermi momentum is symbolized by Pf, will be, so we are talking about number density. So, the total number of cells and then divided by the volume, right. So, you are integrating this equation, and since you divide it by volume, V appears no longer in this integrand, but you are integrating from 0 moment p of 0 to all the way to the Fermi momentum Pf. Okay. And so, when you do this simple integration, you get the number density scaling like the cube of the Fermi momentum. And Fermi momentum, remember, is basically you have these multiple energy levels available to the electrons, and there are lots of electrons in a white dwarf, and but you are occupying these energy levels ground up. So, at the ground state and above, totally degenerate, and then you go up to the point where you have exhausted all your electrons, and then the electrons in the highest energy level will have momentum equal to this Fermi momentum, and through this expression it turns out to be proportional to the cube root of the number density of electrons. But the interesting thing is that this itself is independent of the mass of the electron. Now, for white dwarfs, you can show that this gives a relativistic speed for the electrons. So, it is important that you are solving these equations respecting relativity, but the gravity is still relatively weak. So, Newtonian gravity will give you approximately good answers. So, you can just solve in the Newtonian hydrostatic equilibrium equations for this problem to figure out the pressure and density, provided you allow for the momentum of these electrons to be relativistic, which means when you calculate the energy density of these electrons, you again integrate from momentum of 0 to the Fermi momentum 8 pi p square by h cubed, but for energy you use not just m c square. Here c is set to 0, by the way, not 0, c equal to 1, but you actually also include p. So, this is the relativistic expression for the energy when c is set to 1, right, square root of p square plus m square. If you want to bring in c's here, at least in this parenthetic expression, you should have p square c square plus m square c to the 4, and then the square root of for that for the energy. So, now the first law of thermodynamics tells us if there is no change in entropy, then P dV should be compensated by the change in any heat. So, P rather sorry. So, I am assuming that there is no change in the no heat being supplied to the star or no heat escaping the star. So, under that approximation, the change in the internal energy of the star, that is d rho v, has to be compensated by the work done by the star P dV. So, this is the equation that allows us to then use the expression for rho to give the pressure of the star in terms of this derivative of the Fermi momentum with respect to the volume and the density. Okay. So, just the previous equation then and the first law of thermodynamics leads to this pressure density relation. So, these two equations can help us determine the equation of state of the star, in this case a white dwarf, which can be solved with Newtonian equations of hydrodynamics, since the density is less than about 10 to the 10 kilograms per meter cube. And this is what leads to Chandrasekhar's celebrated limit, which we may have studied for example, in your course in statistical mechanics, that the mass limit for white dwarfs that are supported by electron degeneracy pressure is about 1.44 times the mass of Sun. Okay, if the core is heavier than this value, then it will collapse further and cannot be supported by electron degeneracy pressure. For neutron stars, what is active for that support is neutron pressure. Neutrons are heavier, which means that one can afford to have a star that is more dense, more massive, and supported by a stronger pressure, namely the neutron degeneracy pressure. So, the central density of such stars can reach up to about 10 to the 16 kilograms per meter cube. So this happens when the initial star, as I said, is much heavier than the case for white dwarfs, and in such a situation the electrons in the core will of course be relativistic, but they can be so much relativistic that they will combine with protons to produce neutrons. And so this is of course an electron capture process, and this then creates more neutrons in the core, converting from protons, and then allows for the origin of the neutron GGC pressure to support the weight of the star. The same equations that I showed earlier will hold, except that of course Newtonian gravity will not be correct to apply. The gravity here is very strong. So you will have to use the TOV equations as I described before. So a 1.4 solar mass neutron star, for example, has a radius of around 10 kilometers. In comparison, a white dwarf of the same mass has a radius comparable to that of Earth's. Okay, and neutron star masses can range somewhere between 1 to 3 solar mass. So these are all in astrophysical scenarios of cases where the star burns out its nuclear fuel, leaving different remnants behind. You may ask, well, why not heavier masses? Because they cannot be supported by neutron degeneracy pressure. So in that case, they will collapse to form a black hole. And stellar mass black holes are indeed produced as remnants of stars with initial mass greater than 30 times the mass of Sun, and neither the electron nor the neutron degeneracy pressure discussed above is able to prevent complete collapse to remnant in that situation. So for black holes, yes, we have observed not just black holes. Some of the first black holes were observed through X-ray emitted by material that they were accreting from, say, companion stars. But we have lately observed black hole mergers through gravitational waves, and this is a simulation, and hopefully I'll be able to play it. Okay, there you go. So this is a simulation produced by the SXS collaboration that I had introduced in my first lecture. So these two depressions indicate the locations of two black holes, and as these two black holes orbit each other, they lose energy through gravitational waves, and the strain of those waves is shown here at the bottom in this panel, and that strain the instantaneous amplitude and frequency of that strain increases with time, and eventually the black holes merge to produce a common black hole, and the final waveform is that of the ring down of the quasi-normal modes of that common black hole. So let me wait a bit for this animation to play out completely. So this is where the common horizon forms, and then this object rings down to settle into a rotating black hole, and that rotating black hole will not be a Schwarzschild black hole. It will be what is called a Kerr black hole, something we have not discussed here, but that is again an assignment you can take up for further study. Waves from such an event were observed in September, but also subsequently close to a dozen times by the LIGO and Virgo detectors. So these objects exist. We have also observed two neutron stars merge. This was in 2017, August 17th, and we have used the observations of those gravitational waves to be able to probe what the equation of state of neutron stars is like. So how do you do that with gravitational waves? The idea is that so what I am showing here in 3 panels are gravitational wave strains from neutron stars with 3 different equations of state, all the way from soft to medium to stiff. A soft equation of state is one where the star, in this case a neutron star, exerts to little pressure for a given density, whereas a stiff equation of state is one where the pressure exerted by the star is large for that same density. And in this right plot, I show multiple equations of state with various acronyms coming from the different nuclear physics models or physicists who came up with these equations of state. SQM, for example, is strange quark matter. MS is Mueller and Serro after the proponents of that equation of state, and so on and so forth. So, if the pressure exerted is not very strong, then the neutron stars are, relatively speaking, more collapsed. They are less spatially extended, which means that their waveforms are consistent with waveforms produced by even 2 point particles or or 2 black holes moving around. Okay. So, for reference, we show these dashed waveforms of the 2 gravitational wave polarizations plus and cross for those point particle in spiral cases. In solid lines, I show the 2 polarizations produced by gravitational wave emission by 2 neutron stars. In the bottom panel, when the equation of state is soft, these waveforms are more consistent with the point particle waveforms. As you make the equation of state more stiff, so more pressure, and therefore the neutron stars are more extended, you notice how the peak amplitude close to merger gets muffled, and similarly this ring down gets more extended into some post merger oscillations of a remnant neutron star before it presumably collapses to a final black hole. So these are of course hypothetical simulations. In nature, we want to find out which of these equations of state actually is valid, right. So this is an idea of how you can do that. So this is a research idea, that we can use these gravitational waveforms to be able to tell whether the neutron star equation of state is very soft or very stiff. This is very fascinating because it tells us how matter behaves in its densest form before it knows nothing else to do but to collapse to form a black hole. So, what exactly can you extract by looking at this waveform? What you can extract is known as the tidal deformability parameter, this big lambda. So, let me explain in a couple of lines what it is. Basically, when 2 neutron stars come close to each other, they get tidally deformed because each neutron star is responding to the tidal field of the other, and I explained tides in my previous lectures, right, in the form of 4 balls that are falling in the gravity of Earth, right. So, the vertically separated balls will get more and more separated as they fall, the horizontally separated balls will come closer. So, that is a manifestation of the tidal field of Earth. So, because of that, even neutron stars in the company of other black holes or neutron star or other companion stars can get tidally deformed. When the 2 neutron stars are very close to each other, their tidal fields are very strong. So, the deformation are as strong as you can hope for before maybe they get disrupted and then eventually merge. So, the tidal deformability, this big lambda, which is expressed in terms of, actually let me just backtrack. So, if Eij is the tidal field of a star, okay, or a companion, where Eij is nothing but the double derivative of the Newtonian potential phi with respect to spatial xi xj, and Qij is the quadrupolar moment of our friend, our neutron star that we are studying the deformation of. So, Qij here is proportional to the tidal field through a factor that is lambda. This negative sign shows that this is sort of like Hooke's law. So, there is a restoration force. Now, if lambda is large, that means that the tidal deformation will be large. Okay. So, which is for the same mass consistent with the scenario where the equation of state is stiff. If lambda is small, the equation of state is soft. This lambda is not dimensionless because Qij and Eij have dimensions that do not cancel out. So, you can define a dimensionless quantity, this big lambda, as small lambda divided by the 5th power of the mass of the neutron star, and the value of this for realistic stars is between about 100 to 100,000. So, we want to measure from gravitational waves what the lambda, the tidal deformability parameter big lambda is, whether it is 100 or 1,000 or more. And indeed, recent observations have been able to constrain this. Okay, K2 here is the second love number, which tells us ultimately how rigid a star is to tidal stresses. So, and that now brings me to the last couple of slides. In these slides I show plots from the research papers of the LIGO-Virgo collaboration, where the equation of state of this neutron star involved in the merger was studied. The event was called GW170817. The first 17 here is the year of discovery, 2017. 08 is the month of August, and the last 17 is the date in August. Okay, so here we plotted lambda 1 versus lambda 2. So these are the two tidal deformability parameters, dimensionless, for the two neutron stars. Of course, they should be consistent, and you notice that the values are going from tens to thousands, not hundreds of thousands, because for neutron stars lambda is actually not that stiff. So it is more on the soft side, and these colors show the posterior values, with this dashed line being the 90% region on the posterior, and this second dashed line being the 50%. And these other tracks are for different equations of state, like MS1 for the Mueller-Serre equation of state I talked about earlier. And our 90% confidence region actually makes it highly unlikely that neutron star equation of state is like MS1 or MS2. But this is again a case of scientific method in application. It's great that there were physicists like Mueller and Serre who proposed these equations of state, and now with observations we are able to test whether those hypotheses are correct or not correct, or borne out in nature or not. Okay, H4 is another one which is on the borderline in this plot. SLY, APR4 are equations of state which are softer, and they seem to be more consistent with this data. For this plot, we used a neutron star spin in this dimensional spin parameter value of less than 5%, which is not inconsistent with what we find for neutron star spin. We expect these neutron star spin in double neutron star systems to be somewhat on the smaller side. This is based on observations of galactic double neutron star systems, but theoretically they can be larger than this, and if you allow for chi to be tens of percent more, then these posterior curves change and become more elliptically distributed like this. So here the limit on chi was allowed to be almost as high as 0.9, which is more consistent maybe with some black hole spins, maybe unrealistic somewhat for neutron stars, but still we used the gravitational wave data and allowed that hypothesis to draw up these posteriors. So this brings this set of lectures to a close. Of course, the neutron star equation of state has been constrained, but there is scope for more. For example, there are X-ray observations also of accreting systems, neutron star systems, that have been able to constrain the equation of state. Now, the two sets of observations, it is interesting to see how they are consistent with each other, or there is tension between them. If there is tension, that is maybe even better, because then there are problems to work out and solve, new observations to plan. So similarly for black holes, we have observed multiple binary black hole systems already. These allow us to test whether predictions of Einstein gravity are actually correct, especially in the strong field limit. Remember, solar systems tests don't quite allow us to do that. Black holes that are in X-ray emitting system give us some handle through those X-ray observations, and that is excellent as well. But gravitational waves are now new probes that we can add to our armory to complement exercises that are already ongoing with other tools, to be able to ultimately understand things like the nature of gravity and the nature of some of these compact stars. Thank you.